If it comes to the accuracy, I think the most important one is the particle size. Through simulation, you can decrease the number of physical tests. Testing is very expensive. It takes a long time. You have different measurement systems which are very expensive. You can very quickly go the wrong way when you have the wrong settings. Most times you have the speed in rounds per minute, and in calculation you have reads per minute. So we have to calculate it in the right way.
All right, I think without further ado, let's get started, Christian. So welcome everyone to a new episode of the Engineer Mind podcast. Today I'm very excited to have Christian Bauernfeind in the show, and today we'll explore how simulation is transforming design and development at ABM, from thermal management to gear efficiency. So welcome to the show.
Hi, thank you. Thanks to be here.
Really cool. So maybe you can give us a quick introduction to yourself. Who are you to begin with? What are you doing at ABM? And what is ABM in the first place?
Yeah, my name is Christian. I've been at ABM since 2012. That was during my first studies. I wrote my bachelor's thesis here, and after that I joined the test and simulation team, which depends to the R&D department. I was responsible for developing new test benches, test methods, and supporting tests and simulations.
Really exciting.
Today I'm the leader of the test department.
Super cool. So you can definitely give us some insights in today's episode. How do you combine maybe data-driven methods with experiments? But we'll talk about it later on in the podcast. What is the actual mission of ABM? So what do you guys actually work on a day-to-day basis?
Yeah, we develop and produce complete drive systems as a motor, gearbox, and brake, and all from a single source. And we want to be a key player when it comes to customer and application-specific solutions.
Mm-hmm. I mean, this is probably interesting for the audience listening to this podcast. How do you combine or do cross-functional team collaboration between R&D? We mentioned it right here from the testing department, but then also simulation. Mm-hmm. So how do you ensure a culture where everything kind of tightly fits together and so everything is streamlined? How do you do that at ABM?
We are in direct contact when it comes to new projects and new ideas or some problems, and it's a good exchange of all departments, and that's the important thing.
So how would you then define at ABM what drives innovation and competitiveness? How do you stay ahead of the curve?
We are a manufacturer, and we manufacture various parts ourselves, so we can easily track the quality of our parts and get sure that the quality is on a high level, and we can react very quickly and manufacture new products and parts.
Yeah, I mean, when we talk about Christian, competitiveness in today's market, I mean, probably the keyword China speed. Some people in the audience might know the keyword China speed. We have to develop the same amount of quality or even better quality with less resources, right? So ultimately, you will get to the point where you have to decide, are we going to use AI or not? So how do you decide at ABM if a method such as maybe reduced auto modeling or let's say general AI is a feasible, let's say, option to explore?
Yeah, we want to use up-to-date simulation tools and other programs, and so we, when we have something we want to try out, we have key users who are testing it fast, and then we say, okay, it could be a helpful tool. We decide to roll it out and take it in the normal processing.
I think one important follow-up question there, Christian, would be in terms of AI methods. I mean, there's so many methods out there, right? We talk about deep learning, reinforcement learning, machine learning in general. Is how, from a testing perspective, as a test engineer and simulation engineer, do you pick your methods? Because there's so much noise out there, right?
We have to inform us and look out what can be helpful for us. And this is the point. It's very deep information, and when we want to solve a problem, we search for the right tools, and when we have the right tools, or think we have the right tools, we have to test it and take them in our normal working process.
Yeah, I think what you said, Christian, is very interesting because you said when we have a problem, then we look for tools. I think a lot of people do it the other way around. They see a fancy AI tool and then they use the tool without even having a concrete problem. So actually you take the more sane approach, which is we have a problem that needs to be solved in a very fast amount of, or short amount of time. And then you actually find a tool that fits that problem, right? So basically go the correct way, but the opposite way.
Sometimes we go this way and sometimes we go the other way. So it depends on the problem and it depends on the KI tool.
Yeah, I see.
There's something like Copilot or something like that. We use it, but when it comes to simulation tools and AI simulation tools, we have to search for the right thing and for the right solutions we want for the problem.
So when we talk about simulation, I would be interested in what types of tools are you using in the simulation space, because the majority of the listeners are in the simulation space. And obviously, they would be interested not only hear about theory, but also what do you do or what do you use on a day-to-day practice, so to speak, right? What the actual engineers do in the real world.
We use the normal tools, to calculate the shafts, the bearings, and so on. And on the other side, we use tools for FEM simulation and CFD simulation.
Okay, to be more concrete, what do you use for FEM? If you can share it, obviously, and then what do you use for CFD simulations?
At the moment, we use on this workbench for FEM simulation, mechanical structure, and for CFD simulation, use dive.
Okay, Dive CAE, got it. From the design concept to the actual prototype, can you maybe explain for the FEA and the CFD bit is probably very similar. How do you incorporate the simulation tools? Going from the initial design phase to the prototype to the actual testing. How would you actually do that?
You use the FEM for simulation, different loads on different housings and different parts. So we took the best prototype and the best designed house, and then it goes to manufacture a prototype and test the best prototype from the simulation or the best two prototypes of simulation. And with the CFD simulation, it's very similar. You have different housings and different forms, or different operation points, which comes from the application, and then you can compare in a simulation prototype 1A, 1, 2, 3, 4, 5, but you can't build them all and test them all. So you took the best ones and manufactured and make the tests. After that, make the physical tests.
Got it. Okay. What made you actually choose? I'll be quite interested because I've used Andes before, I've used Dive before. Why did you choose Dive CAE for CFD purposes? What makes it so special, especially because it's using an SPH solver behind the scenes, right?
Yeah, we had it comes from our from other projects. We thought a CFD simulation could be very helpful because it was a special project. So we searched for a tool, but we had not the hardware, we had no software. So we searched for a supplier and we found Dive. In the first step, they helped us to do the simulation, and after that, we said, okay, that's a very great tool, and it could help us in our projects too. So we want to get it.
I see. What then are you actually concretely simulating? Is it then thermal, fluid, and structural behavior? Probably not structural behavior, but more like thermal and fluid behavior using the SPH approach, and then more on the structural side of things to use Andes workbench. Is that correct?
That's correct. Yeah.
Did you do also some kind of co-simulation that maybe you take the fluid results and feed them into the structural simulation or vice versa? Or how does that work?
Today, not. Today we have on one side the FEM simulation and on the other side the CFD simulation, and put them manually together and see what is the best case.
I see. Okay. Now, what would be interesting is, especially for the CFD and FEA application, is can you name a couple of simulations or concrete use cases, if you can, of course, where you directly influence the design decisions, but also saved time and accelerated time to market?
Yeah, for example, we developed an oil-cooled electric motor with a new cooling concept. And in this application, the windings are directly sprayed with oil to reduce the temperature. And there are so much things you have to think of. What's the diameter of the nozzle? Where should they spray the oil to? And we did a lot of simulations to get the right prototype. And after that, we think we had the right solution for this new cooling concept, because we had before simulated, okay, when the oil comes in front of them, it's not so good, or it only comes from the bottom or from the top. And what's the volume flow, what is necessary to cool it down. And we did a lot of simulation in this case and helped us to get the right prototype.
I see. Super exciting. I mean, for CFD, what would be the key parameters or let's say output quantities that you're having a look at? For example, pressure loss, heat transfer. Is there anything else that's interesting for you as a simulation engineer?
In one case, we analyzed the hydraulic losses in a single stage sprue gear at various oil levels and speeds. And there we changed the oil level, change speed, and switch off the system, let it roll out. There we measured the speed and the time, so we could calculate the hydraulic losses. And then we compared it with simulation, because when you have too much oil inside your gear, the oil losses increases very. So that's a very current theme for us, because we want to have efficiency drives. So when the hydraulic losses are too much, it's bad for the whole system.
Got it. Apart from the hydraulic losses, any other output quantities that you have a look at regularly?
On a current project, we have a motor on the test bench with housing cooled electric. It was a housing cooled electric motor. So we have to determine the performance data, and then we measure the volume flow, the temperature of the incoming and outcoming liquid, the pressure. And even this we compared with simulation, and it was very exciting because the accuracy was very high, and we could see the trends. Okay, we have more volume flow, we have more electric power, and we could then simulate too. And that's for new development projects very cool.
Yeah, exciting. I'm interested from a simulation point of view, Christian. Which parameters in the simulation, when you use, for example, CFD, this is something I'm more have more love for, the particle size, the kernel functions, etc. Like, what parameters did you tweak to actually get a very high or highly accurate result? Or did you use the standard settings, or what did you actually tweak as an engineer to be able to get such accurate results in CFD?
There are a lot of points you can affect the simulation, but if it comes to the accuracy, I think the most important one is the particle size. The accuracy of your results most times is higher, but there's a line, and the particle size don't have to be more little. Or then there are other effects too. You can switch on surface tension or heat transfer. Viscosity of the oil is an important point, or the density. So you have to set the right parameters of your oil, of course, but even of the setting that you have the right results.
Got it. So the follow-up question would be, I think would be very interesting for all the juniors listening to this podcast. How do you then validate your simulation results against experimental data? Is it very straightforward, or do you use any special methods? How do you do that?
Most times we we do the test, and after the test we do the simulation, because most times the test bench or the test is not so easy like the simulation. Your simulation you can do very quickly. You can set the parameters in another way, but you have on a test bench, for example, the temperature of the room is very important, because with the temperature, the density and the viscosity of your oil is another. So when you have a hot day, it could be at 25 degrees, and the other day there could be 80 degrees. You can't affect them.
Yeah.
So most times we do the test, because then we know, okay, exactly the conditions we used to, and can go with this data set in the simulation.
Yeah. Are there any?
And compare it.
Makes sense, Christian. Thanks. Are there any things that you, as an engineer, have to take care of in terms of like matching these two different data? I mean, you mentioned a couple of things that you, for example, humidity, temperature, etc., like of the environment. But is there anything else where people or engineers could make a mistake when trying to validate the simulation results against testing results or experimental data?
Yeah, of course. First time you have to take the right oil and the right the right conditions and the test parameters, because the simulations only so accurate than your parameters you put into it. You can very quickly go the wrong way when you have the wrong settings.
Got it. Understood. Is there anything else where would you maybe give the audience an advice in terms of what mistakes not to make in terms of like setting up a CFD simulation, or maybe working with experimental data? Maybe something that you've learned during your thesis or during your career as an engineer, something that you could give as an advice to the audience.
Yes, of course. For example, you have to calculate the right speed. Most times you have the speed in rounds per minute, and in calculation you have reds per minute or reds per second. So we have to calculate it in the right way, and for example, the gravity or so on, or the filling has to be good. That's the point. Failures can get very quickly. Yeah.
Got it. What do you think is the most rewarding use case or story that you've worked on at ABM? Something that you are really, really proud of in terms of simulation?
Through simulation, you can decrease the number of physical tests. That's very important, because you have to design a new prototype, you have to manufacture it, and then you have to test it. Some tests takes more than 30 days or 60 days. So when you design something and you design the wrong thing, and the time until the test is end, and okay, it was a bad test, it is very expensive of time and expensive of money. So as I said, you can compare in a simulation a lot of prototypes and take the one or the two who have the best results. So the probability of missing is very low.
When you use simulation, sometimes you cannot identify real blind spots, maybe during testing, right? So are there some cases where you could, using simulation, for example, the SPH method, using Drive, expose hidden issues, for example, thermal hotspots or unexpected pressure losses, for example? Was that the case in some simulations?
We had, for example, a case, we had a pressure valve, and we didn't know, okay, comes leakage from there or from another place. So we did a simulation and saw, okay, and some operation point, the valve is completely filled with oil, and when the pressure gets too high, of course, the oil can get out of this. So we said we saw that, okay, that could be a problem.
This is super insightful, Christian. So what I would be interested in is maybe talking about efficiency gains and maybe cost savings, like explicitly. So how has simulation concretely reduced the need for physical prototypes? Do you have a concrete number for it or maybe a percentage?
I think it's over 50%. When you have different applications and different prototypes, I think when you do it or want to do it right, you have to do many tests especially when it's an application you haven't very experienced for it, and it's a new case with new operating conditions and so on. So I think in such case where the failure possibility is very high, you have to do a lot of tests, and with simulation, you maybe don't have to do such or a lot of tests.
In terms of like approaching the simulation, you have one large simulation. Do you also use the approach of subdividing it into smaller simulations, like sub-simulations? How do you approach simulation per se?
We had cases where we simulated the whole system, and then we saw, okay, there's a special point of interest, and could there build a sub-simulation with the other particular size or small particular size, so that we can have a deep sight inside. So and analyze the problem or the point of view more accurate.
Okay, Christian, then do you believe, I think it's more like a trivial question, like where the findings had changed your understanding the fluid behavior and thermal behavior of your components? So I mean, if you compare kind of the experimental side of things versus the simulation side of things, how did simulation influence your understanding of both worlds?
In most cases, you can see inside your gearbox. So it was always a black box, and okay, sometimes you think it would happen, but when you see the simulation, especially with higher speed levels or so on, there things were happening you never had think of it. So there were some surprises you only see with the simulation, that fluid or oil or something act like this.
I see, understood. I have one question.
Or attracted to, yeah.
Yeah, I have one question, Christian. When it comes to the simulation tools, I would assume you used something before Dive or before Workbench. I'm not sure how you started, but can you maybe talk about, if you obviously can share it, why have you decided to then switch CFD tools? Or was Dive the initial start to use CFD? Because I would always be interested in what was the motivation to change from one tool to another, because as we engineers know, never change a running system. So why would you change the CFD tool to begin with? Is it the GPU power? Is it the speed? What was it that made you decide to go a step further?
Dive was our first simulation tool of CFD, and through our project with Dive, we saw, okay, wow, it's a very cool tool, and it could help us in our standard engineering process. And then we say, okay, hey, come on, let's try it out. I think you can do a lot of things and a lot of simulation things and special things you can't do without it. So I think it's a great tool, and will change the way we develop something.
Mm-hmm. Now the question is for future outlooks. I mean, when we talk about AI, reduced auto modeling, digital twins, right? There's even extendable digital twins, I believe. How do you anticipate the future is going to look like, Christian, especially for ABM? Are you exploring something in this area, like AI, for example?
AI, I don't know, but our goal is to have a digital twin, the virtual presentation of complete drive, even before prototype construction. And we want to expand the simulation for lubricant and cooling analysis in new product lines. So I think the simulation tools are a very important part of the future developing process.
I'm interested in what you think. What what makes you most excited about the next 3 to 5 years when it comes to engineering? Could be simulation, could be testing. Like, is there any trends that you see, or maybe at ABM even, that you work on or maybe do research and development on that really excite you personally as Christian?
Yeah, I think simulation will be a bigger part because testing is very expensive. It takes a long time. You have different measurement systems which are very expensive, and the time on the test bench itself is expensive too. So I think to set up a simulation and simulate it and have then results and good results will become more, because it's a very good way to spend money.
Yeah, absolutely. What would you advise if people have no idea how to get started with simulation? Do you just, we mentioned it earlier in the podcast, do you just pick a problem and then solve it? Or how would you approach such a problem? I mean, you're an experimentalist from what we heard. How do you approach simulation? Like, is it just trial and error, fail a lot and then, or fail fast and fail quickly? Or what would your advice be to the audience?
We try to take the right input, to have the right informations to do the simulation. And then I think we have great solutions or great results.
Excellent. I think that pretty much covers it, Christian. Thank you so much for the insight, because people are asking why we do this interview. I think it's always nice to hear from the practical side of things, how simulation is being done, because we have so many academic podcasts on this channel. So I think it's always great to have people from the industry talking about how they use simulation, but also experiments, and maybe both in synergy. So Christian, thank you very much for being on the show. And maybe last question, who should reach out to you and who should work with ABM?
I think when you're a customer and need a specific solution for a specific application and not a standard product, I think we are the right supplier for you.
Excellent. I will put every relevant link, maybe if you can share some other links that are relevant for the audience in the description so people can check it out. For example, Antis Workbench, Dive CAE, which is one of the best tools out there in the market when it comes to SPH. Again, Christian, thank you very much for your time, and maybe, who knows, we'll see each other in a second episode in the future.
Yeah, thank you.